Okay, hey guys, I think this is the first video set after the quiz. Anyway, the professor already gave you your average and mean. I just thought you might want to see a distribution of the grades. Yes. The average is right here. This is the 16, so you can see that most people, there's a big clumping right above the average and then a little bit below the average. Yes, so exam, again, not what I expected. I actually think it was a little bit harder than quiz 1. Which I guess is reflected in your results, but I knew as soon as I saw frames that this was going to be a problem, and I'm sorry for not preparing an example on frames. I hadn't been expecting frames for a number of reasons, but yes. Anyways, congratulations to those who did well. If you did not do well, there is still a final. We will be having a final. There will be no final project. Yeah, if you want to go over your exam, you can feel free to see me. I don't have solutions ready for those. Mostly because well, the professor has solutions, but he hasn't given them to us because we still have a number of students who haven't taken the exam yet. But yeah, well, feel free to stop by if you want to go over it. I'll see what you did, and might be able to work something out. Oh yeah, a number of people were asking about whether this exam will be curved or not. I honestly do not know for certain, but I suspect that the professor will look at grades at the end of the semester and will curve them accordingly as opposed to curving any particular exam. Which is usually better, I think, but it does cause some uncertainty before until then. Anyway, yeah, I just wanted to show you this. If you have any questions, let us know. Yes. Okay. Anyway, for tutorial 8 is actually extremely short. It's one of the shortest homeworks you guys have ever had, so you really do not need more than what, a week? You guys have a week to do this. If you have questions with this, just stop by and see one of us. I think the professor will go into a lot more detail for some of these things on Friday. He hasn't gone over the truss yet, and I'll make a separate video for the truss. I just wanted to give you some basic. I'm not going to do these examples. I think you did enough examples in class, but I'll just show you how to use how to solve these kinds of problems. I strongly recommend you use Muller-Breslau. Muller-Breslau. I think I'm pronouncing that correctly. I find it to be utterly amazing. I don't know about you guys, but it's like, oh wow, I can't believe that actually works. But yes, I think there's some confusion on a couple things, like how to model shear and how to model moment. So I will say that I've never learned influence lines before, so this is new for me also, but as you guys can see, it's very useful. Anyway, I just say that now in case that I have a feeling that I'm probably gonna say some things that work, but not necessarily for the reasons that I state. And yeah, that's just because I'm still learning this myself. So anyway, you basically have oh yeah, for Muller-Breslau you have, if you want to find reactions, let's say I'll be working with a simply supported beam for all my examples. So if you want to find a reaction, you start off with your simply supported beam and you just you lift whichever point you'd like to find the influence lines for the diagram or for the reaction you're at. So if I want to find the influence line at A, actually, let me draw these in line. And this becomes my influence line. So I have maximum 1 over here, 0 over here. This should be obvious. If I look at the more analytical approach, and I just have a virtual load that's applied at some distance x. When the load is right here, I have a maximum. When the load is over here, I have minimum. Right? Because if it's right over here, all the load is being transferred to the reaction. If it's over here, all the load is being transferred to this reaction. And if this is carrying all the reaction, this has to be 0. So you can just draw your points. Calculate this if you actually want to. But I find Moeller-Breslau to be a huge time saver. Anyway, that's your reaction. As usual, we'll now look at shear. Shear is confusing, I think. I don't know if there's a good explanation for this. I'll just say that for shear, imagine that you're cutting the beam. So imagine just like, let's say, you're usually interested in finding the shear at some length. Let's say you just, oh, I'm sorry, I need to, no, this is fine. You're usually interested in finding the shear at some point. Let's say we're finding the shear at the center. I'm just gonna cut it at the center. So I start over here, just cut it in the center. And then I say, well, let me lift one side and lower the other side. So I do this, and I end up getting like this. And that should be your diagram, I think. I need to double check some things on this, but I'm fairly certain that this is correct. So for example, when you have a traveling load that's over here, the shear in the middle is 0. Let's call this point C, A, B. When you have a point here, your VC is going to be plus or minus, I'll just call this 1. And if you're all the way at the end, you're going to be at 0 again. Anyway, yeah, just remember that for shear, you cut and rotate. Like I'm cutting this in half. Or you don't necessarily rotate, but I'm cutting and then displacing. Last one is moment. Moment is unusual, shall we say. For moment, you start off, and then you just apply a bend to it. So, for example, if I draw this, by bending it, you want to literally just bend it, or it doesn't. You're interested in the shape of your moment diagrams. You're not necessarily interested in signs. So yes, and then I'll just specify that for this case, note that when you displace something, you have to maintain its original. You have to maintain your boundary conditions. So when I displace this, I don't actually, I just lift the center point up. So like over here, I have it flat. in this case I'm saying, well, let me lift this point up, but do you agree that I could just say, well, let me pretend that this is actually still on the ground, but then let it sink, if that makes sense. So you end up with something that's shallower. Like this angle is not as big, but it's flat. So that's what happens here when you apply this bend to it. You end up getting something that looks like you have a big triangle, which is what you'd expect. If your point load was in the middle, you develop maximum moment. If your point load is all the way at either end, you develop zero moment. Yes, as for actually calculating these values, remember that all your diagrams are based on a unit load. So for example, up here I applied a unit load of 1. The maximum I would get in this case is 1. I will say that the maximum you get does not have to be 1. In this case it is, but in, I believe it's this problem, your maximum value will not be 1. Your maximum value will be larger than, it'll be larger than 1. For, I'm sorry, your maximum vertical reaction a day will be greater than 1. That's just something to keep in mind. But yeah, that's pretty much it. Let us know. Oh yeah, sorry, I was just calculating these values. We only usually worry about the maximum case, because once we just need to label the maximum and minimums of our triangles, and then we're set. So the maximum that occurs here, well, if I put a unit load of 1 here, what are my reactions? It's 1/2 and 1/2, right? Because it's symmetrically loaded. I'm putting it right in the middle. I have 2 reactions that are equally spaced. Therefore, my reactions have to be equal. And then if I look at my length, the whole thing is length L. The whole thing is length L. So this length here is L over 2. This load is 1/2. Therefore, this is L over 4. And this is exactly what the professor did in class. Yes, so that's pretty much it. Again, over here, your reactions are 1/2 and 1/2. I'll use the same color. So this is 1/2, this is 1/2. What was my point here? Yeah, so the maximum here is 1/2 and negative 1/2, I believe. You want the difference in your 2 shears to be 1. So yeah, just let us know if you have any questions. Remember that these are not, just keep in mind that these are not moment of shear diagrams. And like the professor was saying, if you keep that in mind, then you shouldn't have any problems. Okay, so this time actually, this is the last time. Let us know if you have any questions.